Hello, everyone. I'm Weida Hu. I'm a graduate student from University of Science and Technology of China. I'm working with Junxian Wang from USTC on the Epoch of Reionization. Uh, I would like thanks to the uh, I would like thanks to the organizer for this opportunity to present our recent work here. Uh, my the title of my talk is Lyman Alpha Protocluster, the redshift 7. Uh, this is the outline of my talk. First, I will introduce a little background about the realization and the Nagel survey, and second, I will present the discovery of a protocluster redshift 7 and its properties, and last, I will summarize my talk. So, Galaxy clusters are the largest structure in the universe and has been extensively uh, used to constrain the cosmological parameters and to investigate the galaxy evolution in mature environments. However, the formation of the cluster is not well understood, so it is it is essential to investigate them when they were young. That is in a protocluster stage. Numerical simulations have predicted the protoclusters can significantly contribute to the cosmic star formation rate density with fraction up to 30 to 50% at redshift 6 to redshift 10. They can provide a significant fraction of ionizing photons and may be crucial in driving the timing and topology of the realization. Previous talks have shown that the quasar uh, uh, could be an excellent probe of the epoch of realization. Lyman alpha emitter galaxies can uh, also be a powerful probe uh, when the Lyman alpha photon emitted by the galaxies passes through the intergalactic medium. It will be resonant scattered by the intergalactic medium, and the observed spectrum can reveal some properties of the intergalactic medium. Uh, for example, we can study the line profile or the line luminosity, the observed line luminosity to determine the uh, neutral hydrogen fraction of the intergalactic medium. So we carry out a narrowband imaging survey to search for Lyman alpha galaxies in the epoch of realization. The survey is named is named the Nagel survey. We designed a narrowband filter to search for Lyman alpha emitters at the redshift 7. We optimally designed the filter to avoid the strong sky emission lines and atmospheric absorption. We can use this filter to search for Lyman alpha galaxies in the redshift range of 6.89 to 6.97. The narrowband filter was installed on the dark energy camera on Blanco 4-meter telescope. The dark energy camera has a very large field of view and red sensitive camera. Its total response at about 19,600 angstrom is still larger than 15%. So this combination makes the Nagel survey one of the most efficient survey uh, uh, survey in searching for Lyman alpha emitters in the epoch of realization. We aim to construct a unique narrowband selected Lyman alpha emitter sample at redshift 7. We expect to select more than 600 Lyman alpha emitters. The area coverage of the Nagel survey is very large, larger than 20 square degree. It is the largest narrowband imaging survey for galaxies of redshift 7 and above. Uh, we adopt a wedding cake strategy to search for both bright and faint Lyman alpha galaxies. Based on this Lyman alpha emitter sample, we can study the the properties of the the galaxies in the early universe and the history of the realization. So up to now, we have observed the four fields: the cosmos, change-living field, south, gamma, and the wide field. They have selected 174 Lyman alpha emitters, redshift 7, and the recent results show that the neutral hydrogen fraction at redshift 7 is about is lower than 0.33. So the protocluster region was firstly shown some interesting signal in 2017. In 2017, we selected 23 Lyman alpha emitters based on 34 overall narrowband exposure in the cosmos field. Here I show the spatial distribution of 23 Lyman alpha emitter candidates. The size of the circle indicates the Lyman alpha luminosity. If we focus on the bright Lyman alpha emitters with luminosity larger than 10 to 43.3, you can find the 1 and 3 is very close with the distance is only 3.6 arc minute. The bottom shows the pseudo color cutout of this 2 Lyman alpha emitter, where the narrowband is green. Sorry, the what? Narrowband is green. The Z band blue and Y band red. So you can find they are very green and compact. These 2 Lyman alpha galaxies were subsequently confirmed by the Magellan spectroscopic observation. Their high signal to noise ratio spectra shows significant, highly asymmetric line profile. So finding two such bright Lyman alpha emitter galaxies in very close distance is very encouraging. So we decided to take more narrowband observation on this field to figure out the physical nature of these two Lyman alpha emitter. In 2019, we obtained 47 over narrowband exposure on the cosmos field and selected 49 Lyman alpha emitter galaxies. So this plot shows the spatial distribution of Lyman alpha emitter candidates, and the contour shows the galaxy number density. You can see a highly overdense region consists of 40 Lyman alpha emitters. It is identified as a protocluster redshift 7 with overdensity of 5.1. This is the domain spatial distribution. We carry out spectroscopic observation for using Magellan Telescope, and for 40 Lyman alpha emitters from Hu 2019, 11 was spectroscopically confirmed. The volume of this protocluster is 66 times 30 times 26. The overdensity is 5.1. Here shows some spectra of Lyman alpha emitters. So based on its overdensity, we derived its present day mass to be 3.7 times 10 to 50 solar masses. We use several methods to find as much Lyman alpha emitters of the protocluster as we can. Firstly, we 4 lower grade Lyman alpha emitters were identified by the spectroscopic observation. Secondly, we noted that the transmission curve of narrowband overlaps. The transmission curve of our narrowband overlaps with the HIC narrowband, so we stacked the 2 narrowband images and selected 3 more faint Lyman alpha emitters. In total, we discovered 21 member Lyman alpha emitters, and 16 have been spectroscopically confirmed. So the Lyman alpha galaxies, the galaxy in the epoch of realization can produce large amount of ionizing photon and ionize its surrounding neutral hydrogen. So the ionized bubble can grow and merge with the adjacent bubble and into a very large ionized bubble. the protocluster can, in the epoch of realization, can lead the production of such ionized bubble because its high number density of galaxies. We calculate the bubble size of the member galaxies of the protocluster based on relation between Lyman alpha luminosity and the bubble size. We found the total volume of ionized bubble is slightly larger than the volume of the protocluster. This demonstrates individual bubbles has overlapped, and the bubble are in the act of merging into one or two giant bubbles. The intergalactic medium within the protocluster is almost fully ionized. So for this protocluster, we have submitted a proposal to James Webb Space Telescope with to observe with low spec, and we got 35 hours. We are going to observe O2, O3, H alpha, and H beta lines of the member galaxy of this substructure. Please stay tuned for the JLAP-SQ results. So I leave a summary here, and if you are interested in larger survey, you can scan this QR code for the publications. And so thanks for your listening. I stop here and take questions.
All right, thank you very much for a great talk. Let's wait for questions on Slack. While we're waiting for questions, can you tell us more about the JWST program? What are you observing? How many galaxies and so on?
So we are observing the galaxies in this substructure. There are 8 galaxies, and we will observe O2, O3, and H beta and H alpha emission lines to investigate their ISM properties, Lyman continuum escaping mechanism, and so on.
Yeah, we have a question from Yusheng Qin. Can you elaborate a bit on the estimation, on how you estimate the bubble size?
How to estimate bubble size? So we estimate bubble size based on this relation between the Lyman alpha luminosity and the bubble, the radius of the bubble, and we derive the bubble of every member galaxies in this protocluster, and we simply summed the bubble, the volume of the bubble.
I guess the question is that requires knowing some ratio between the continuum or the ionizing flux and the Lyman alpha luminosity. Do you have to make some assumptions about that?
No. So this simulation calculate the bubble base. Yeah, this simulation calculated the bubble size based on the
using that
star formation history and derived the galaxy, the current galaxy, the galaxy Lyman alpha luminosity and the bubble at a different redshift.
Yeah,
we didn't use the.
Sorry, go ahead.
Okay. Oh, go ahead, please.
Just quick question. Yusheng said I probably missed it, but what's the UV magnitude of these galaxies?
What magnitude?
UV magnitude. So do you have continuum measurements?
Some of them were detected in the Y band or J band, so we can derive their UV magnitude based on those near infrared photometry.
Okay. Well, maybe you can give more, discuss more. And Tom Toons asked a question that the observed average density could differ from the actual average density of Lyman alpha emitters if many Lyman alpha emitters are invisible because they're in regions that are too neutral. Would this affect your density estimate?
Yeah, indeed, the overdense region could contain more neutral hydrogen and thus severe attenuation by the neutral hydrogen. On the other hand, the overdense region could have much higher star formation rate, so boost their Lyman alpha luminosity. These two effects could cancel each other. So, however, we don't know which effect will dominate the result, the observed overdensity of the Lyman alpha emitter.
Great.
So I cannot tell the.
Okay, thanks again for a great talk. Let's move on